Okay, for section 10.2, we're going to look at polar equations and their graphs. I do want to kind of forewarn you, everything that we did in the previous section, 10.1, is kind of important here, so you need to remember how to convert between polar and rectangular coordinates, and especially you need to be able to convert between polar equations and rectangular equations, okay? So if you haven't done that or you're not very familiar with that, go back and do that first, okay? Now, as a definition, we love starting out with a good definition. We have that an equation whose variables are polar coordinates is called a polar equation. That makes sense, right? And then we have that the graph of a polar equation consists of all points whose polar coordinates satisfy the equation. That should make sense to you. If you go back to like some generic definition for just a regular old equation in the rectangular coordinate system, like something you would have looked at in Math 171, you would have a very similar definition to this. You would just say, of an equation whose variables are x and y is an equation blah, and then you'd say the graph of an equation is blah, and it's going to end up being all points that satisfy the equation. So we're just kind of plugging in this world of polar coordinates now. Okay, so before we dive into the actual graphing of polar equations, let's review a couple of equations really. Let's review a few equations that are really important that you kind of have a general understanding of here in the rectangular world so that when we see their polar versions, it's not quite so hard to bring them to the surface, okay? Because some of this might be a little dormant because we haven't been in 171 for a while, okay? So in algebra classes, we discussed several common equations. Let's review a few that will be important in this section. So at some point, I want to say it's maybe chapter 3 in your book, you all talk about parent functions, and a lot of these show up then, okay? And if they don't show up at that point, they show up at other times in your course. So the first one you have is just y equals x. Okay, if you have a y and an x to the first power, you know it's going to be a line, and this is kind of like the most generic line. This is a line that goes through the origin with a slope of 1. So let me get my marker. So we go through the origin, and we have a slope of 1, so we're going to go up 1 to the right 1, up 1 to the right 1, up 1 to the right 1, and so forth. We could go down 1 to the left 1, down 1 to the left 1. Essentially, we're going to get ordered pairs that look kind of the same. So -4, -4, -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, so on. And if we connect these points, we get a graph of the solution, which is all of the ordered pairs that satisfy the equation. Okay? Now, for the next one, we have just x equals -3, okay? So at some point in your algebra career, we would have discussed horizontal and vertical lines. And what most students remember is that one of the variables is missing, but they have a hard time remembering which is which. So this is the best way I've gotten my students to remember. We have x equals -3. We are clearly missing a y. Well, without a y, we are not going to touch the y-axis itself, okay? But with this x, we have to touch the x-axis. So how could we exist in the rectangular coordinate system where we don't touch the y-axis, but we for sure go through the x-axis? Well, it would make us a vertical line, okay? So we would be a vertical line that goes through -3 on the x-axis, okay? This just means we're parallel to the y-axis. The only way we could really get an equation like this that's vertical that touches the y-axis is if we had x equals 0. Otherwise, all other vertical lines are going to be parallel to the y-axis, so we're never going to touch it, okay? And then next up, we have y equals 1. So kind of the same situation. We're missing a variable, but what does this mean? We clearly are missing an x. So this means that without the x in the equation, we're not going to touch the x-axis, but we're for sure going to touch the y-axis. So how does that work? How do you exist in the rectangular coordinate system going through the y-axis without touching the x-axis? Well, you're horizontal, okay? So you are a horizontal line that looks like this. So that means you're going to be parallel to the x-axis. You're running in the same direction as the x-axis. You're just never going to touch it unless we have the equation y equals 0. That's kind of the exception to the rule. Same thing up here. We're running in the same direction as the y-axis. So we're going up and down. We're vertical. We're just not going to cross it unless we have that one exception, x equals 0. Okay? And then finally, another type of equation we're for sure going to see its polar form is a circle. Hopefully your Math 170 brain was screaming, it's a circle, it's a circle, okay? This is definitely a circle, okay? But not only is it a circle, it is a circle centered at some ordered pair with a radius of r equals something. Okay, so hopefully you remember the basics of a circle. So when you have a circle in this just like super standard format right here, whatever is being subtracted from x is the x coordinate of the center. Whatever is being subtracted from y is the y coordinate of the center. So our center here would be -1, 2, and we have a radius of 4. Okay, so we could pretty easily plot this or draw this, sketch it, we'll say. So we want to find our center first. So that is at -1, comma 2. So we go back 1 up 2. That's my center. And then, ooh, I hope somebody caught this. My radius is not 4. Hopefully you're at home like rolling your eyes saying like, "Oh, she's an idiot." I'm not an idiot. It is late and I definitely made a goof here. The radius is what? It's 2, okay? So the radius is the square root of whatever this is, okay? So we have a radius of 2. So from our center, we're going to go up, down, left, and right 2 units. So to the right, 1, 2, down 1, 2, to the left, 1, 2, up 1, 2. And I'm so terrible at drawing circles. They always look like lemons. I also feel like this grid is not perfectly square. But just do your best. I'm not judging how good your circles are. I'm judging, do you understand the equations more than anything, okay? So pretend it's a perfect circle, but that's it. So you have had a gentle reminder of just regular old diagonal lines, horizontal and vertical lines, and then circles, okay? And we're going to see polar forms of all of those soon, okay? So that's it for this first one, just kind of a review of common equations. In the next video, we're going to review converting between like polar and rectangular stuff, and then we'll eventually look at these polar equations. And we're going to look at a few just kind of generic ones, and then we're going to look at 4 really special types, okay?